Hello, my name is Sunayana and today we are going to discuss about external data representation and marshalling. These are the topics that we are going to discuss in the following presentation. External data representation, marshalling, approaches to marshalling, CORBA's common data representation, CORBA in marshalling. External data representation. It mainly consists of two questions. Why does the communication data need external data representation and marshalling? This is mainly because different computers contain different data formats. For example, big endian or little endian integer order or ASCII or Unicode character coding. In the example of big endian or little endian, most numbers that you store are larger than a byte and there is some choice about how you lay out multi-byte numbers in memory. In big endian, you store the most significant byte in the smallest memory address, and in little endian, you store the least significant byte in the smallest memory address. For example, consider the expression int j equal to 3. It is represented like this in memory. So, in the big endian approach, it is written from left to right, and in the little endian approach, it is written from right to left. So, the most significant bits are written in the smallest memory address in the big endian approach, and the least significant bits are written in the smallest memory address in the little endian approach. So how to enable any two computers to exchange data values? One of the following methods can be used to enable two computers to exchange binary data values. The values are converted to an agreed external format before transmission and converted to the local form on receipt. If the two computers are known to be the same type, the conversion to external format can be omitted. The values are transmitted in the sender's format together with an indication of the format used, and the recipient converts the values if necessary. The next topic is marshalling. Marshalling is the process of taking a collection of data items and assembling them into a form suitable for transmission in a message. Unmarshalling is the process of disassembling them on arrival to produce an equivalent collection of data items at the destination. Thus, marshalling consists of the translation of structured data items and primitive values into an external data representation. Approaches to marshalling. There are three alternative approaches to external data representation and marshalling. First one is CORBA's common data representation, which is connected with an external representation for the structured and primitive types that can be passed as the arguments and results of remote method invocations in CORBA. It can be used by a variety of programming languages. The next one is Java's object serialization, which is concerned with the flattening and external data representation of any single object or tree of objects that may need to be transmitted in a message or stored on a disk. It is for use only by Java. XML, extensive markup language, which defines a textual format for representing structured data. It was originally intended for documents containing textual self-describing structured data, for example, documents accessible on the web. But it is now also used to represent the data sent in messages exchanged by clients and servers in web services. In the first two approaches, the primitive data types are marshaled into a binary form. In the third approach, the primitive data types are represented textually. The textual representation of a data value will generally be longer than the equivalent binary representation. The HTTP protocol is another example of textual approach. CORBA's common data representation. CORBA CDR is the external data representation defined with CORBA 2.0. CDR can represent all of the data types that can be used as arguments and return values in remote invocations in CORBA. The primitive types used in CORBA are short, long, unsigned long, float, double, character, boolean, octet. And the constructed types are sequence, string, array, struct, enum, and union. So the constructed types and the how we represent it in CORBA is given in the table below. In the primitive types, CDR defines a representation for both big endian and little endian orderings. Values are transmitted in the sender's ordering, which is specified in each message. The recipient translates if it requires a different ordering. The primitive values that comprise each constructed type are added to a sequence of bytes in a particular order as shown in figure. Marshalling in CORBA. Marshalling operations can be generated automatically from the specification of the types of data items to be transmitted in a message. The types of the data structures and the types of the basic data items are described in CORBA IDL, which provides a notation for describing the types of the arguments and results of RMI methods. For example, we might use CORBA IDL to describe the data structure in the message and figure as follows. So, this is the CORBA IDL representation of the example shown in the slide before. So there is name, place, and the date of birth, year. So similarly, there is a remote method invocation done in CORBA for that same example. The CORBA interface compiler generates appropriate marshalling and unmarshalling operations for the arguments and results of remote methods from the definition of the types of their parameters and results. These are the references that are used to prepare the above slide. Now, let us watch a video regarding marshalling so that we can know more about it.
First, let's look at how we can reduce the overhead in marshalling the arguments and the data copying. Just to jog your memory, marshalling refers to the fact that the semantics of the RPC call being made between the client and the server is something that the operating system doesn't have any clue about. So in other words, the arguments that are actually passed between the client and the server has semantic meaning only between the client and the server. The operating system has no knowledge of it. And therefore, marshalling is the term that is used to say, let's accumulate all of the arguments that is there in the call and make one contiguous network packet out of it so that we can give it to the kernel and the kernel can send it out. That's what is being described as marshalling. And the biggest source of overhead in marshalling is the data copying that's going to happen. And I'll explain that in a minute. Potentially, in doing the marshalling, there could be 3 copies involved. Where are these 3 copies coming about? Well, first of all, the client is executing. When a client is executing a procedure, all the arguments for the procedure call that it wants to do is living on the stack of the client. And there is an entity, we've introduced this terminology even before, called the client stub. And the role of the client stub is to take the arguments of the call which are living on the stack and convert it into a contiguous sequence of bytes called an RPC message. So the RPC message has no semantic meaning. It is just a contiguous string of bytes which you can pass to the kernel, and the kernel can then send it out on the wire, just like any other message. So that's the first thing that the stub does, and that's the first source of overhead. The client stub is making the first copy from the stack in order to create an RPC message. Now remember that the client is a user program, so it is living in the user space outside the kernel, and so this RPC message, which has been created by the stub, it is part of the client's address space, which is living outside the kernel. So this RPC message is in user space, and the kernel has to make a copy of the RPC message from the user space into its own buffer, the kernel buffer. And that's the second source of overhead, the second source of copy in doing the marshalling of the arguments. So now it is in the buffer of the operating system kernel. Now the operating system can kick the network controller and say, hey, go ahead, take this buffer, send it out on the wire to the desired destination. And the network controller at that point is going to move the bits from this buffer, which is in the system memory of the operating system, into its internal buffer using DMA. And this is the third copy that is happening. The copy that is done by the network controller using DMA to move the bits of the RPC message copied from the user space into the internal buffer of the kernel, and now this movement is being orchestrated by the hardware to move it from the kernel buffer into the internal buffer of the network controller so that it can then get out on the wire. So those are the 3 copies involved in marshalling the arguments of the call before it can be put out on the wire. And the copying overhead is the biggest source of overhead for RPC latency. Now, how do we reduce the number of copies? Well, it turns out that the third copy that you're looking at here, moving the bits from the system memory into the network controller, this is a hardware action. And this is unavoidable, and therefore we're going to live with it. Unless the network controller is completely redesigned, if the network controller is saying, well, I need to DMA the bits from the system memory into my buffer, well, I have to DMA the bits from the system memory into my internal buffer before I can put it out on the wire, then this third copy is inevitable, so we live with it. But we would like to see if we can try to reduce the number of copies involved here. The first idea is, can we eliminate this copy that is done by the client stub? Why is that happening? Well, it has to create a network message in order to send it out on the wire. As we said, that the semantics of this call is only known to the client and the server, and the client stub is taking the arguments and making a network packet out of it. And it was doing it in user space. And so what we're going to do is we're going to marshal it directly into the kernel buffer. In other words, we've now moved this stub, the client-side stub, from the user space down into the kernel. If you can move it into the kernel, then from the stack, the stub can directly marshal it into the kernel buffer. And so that intermediate copy that we had here, creating an RPC message and copying it again into the kernel buffer, is avoided if the stub can directly work on the stack and write it into the kernel memory. So what this means is that at instantiation time, the client stub is installed inside the kernel. At bind time, when the client binds with the server, at the bind time, what we're going to do is we're going to say that here is the client stub, please put it inside the kernel so that later on you can use that in order to do the marshalling. So the synthesized procedure is installed in the kernel for each client call. So for each client-server relationship, we synthesize a procedure, which is the client stub, install it in the kernel for use every time I make this call. This stub can be invoked to convert the arguments that are living on the stack into a network message and directly put it into the kernel buffer. So this obviously will eliminate from the 2 copies down to 1 copy, because the intermediate copy of converting the arguments into an RPC message is now eliminated. Now the problem with this idea is that we are saying, let's dump some code into the kernel, and that may not be something that is so palatable. So this is a solution that's possible if the RPC service that is being provided between the client and the server is a trusted service, and therefore we can trust who is putting the stub into the kernel. In that case, this solution may be a reasonable one to adopt.